Hi, I'm Matt and welcome back to another video. In this video we're going to be having a look at a few separate things, all related to a computer program that I wrote. In my last video I mentioned that I had used a Python program to calculate the amount of fuel I would need for the Elysium, and in this video I'm going to show you how I went around doing this. So I'm going to talk through the maths, I'm going to talk through the code, and I'm also going to do the demonstration of how to use it at the end. So I hope you enjoy. I will put some times to skip to if you're not interested in certain bits, so if you're not interested in maths you can just skip to the code and the demonstration, or if you're just only interested in the demonstration you can just skip to the installation and the demonstration. So without further ado, let's get into the maths. Right, let's get started. So the first equation we're going to have a look at is the delta V equation. I did mention it in the last video, but if you haven't heard of delta V is the amount of speed that your fuel can create using your engines. Delta V is equal to the natural logarithm of mass total over mass dry times your specific impulse times gravity. This looks like a very complicated equation, but let's break it down. Delta just means change in. That's all it means. It's just the change in velocity. The natural logarithm is a function that takes a number and gives the logarithm in the base of e, which is a number about 2.7. E is one of these magic numbers that the entire universe seems to work on. Your dry mass is your mass total minus your mass of fuel. And the mass of fuel is what we're looking for in this equation. Your specific impulse, commonly written as ISP, is a measure of how efficient your engines are at converting fuel into delta V. And gravity, that's just gravity. For Kerbin it's about 9.81 meters per second. For different planets it's different, but we'll have a look at that later. This is all it is. It's a very imposing equation, but it's actually quite simple when we break it down. Matt, you amazing genius, why is this so useful, you ask? And it's useful for a few reasons. It can be used to find delta V from your mass of fuel, and this is very useful and is the most common use for this equation, which is why it's written to the subject of delta V. If you're using Kerbal Space Program 1.6, you'll have the new delta V calculator inbuilt into Kerbal Space Program, which will tell you how much meters per second of velocity your fuel will give you. And if you're using an older version, you can use something like Kerbal Engineer Redux or one of the various other things, or you can calculate it by hand. In our case, we are using this equation to find our mass of fuel that will produce a certain amount of delta V. So we know our delta V, but we want to know our mass of fuel. So we need to rearrange this equation to get the mass of fuel to be the subject. So to start rearranging our equation, let's just write it out again without all of the annotations. So delta V is equal to the natural logarithm of mass total over mass dry times specific impulse times gravity. So for our equation, we know what delta V is going to be. What we don't know is our mass of fuel, so we need to rearrange this to get mass of fuel on the end. What we're going to do is move the specific impulse over and the gravity over, so we'll divide both sides by specific impulse and gravity. So we end up with delta V over gravity times specific impulse is equal to the natural logarithm of mass total over mass dry. So this is still not in a useful form because of this logarithm. So what we're going to need to do is move this logarithm over. And this is where it gets complicated. A logarithm takes two things into account. It takes the number you want to get the logarithm of, x let's call it. It also takes the base, y. The base is normally either 10 or the magic number e at about 2.7. So we're going to want to move this logarithm over. So the opposite of a logarithm is to raise y to the power of the logarithm of x. In our case, because we've got a natural logarithm, that means we've got to raise e to the power of something. So what we're going to do, we're going to do the inverse log, also known as the antilog, so we end up with e to the power of delta v over specific impulse times gravity. And this is already getting to look extremely complicated. So that leaves us with mass total over our mass dry. So now we're going to times both sides by mass dry. So that leaves us with e to the power of delta v over specific impulse times gravity times mass dry is equal to mass total. And this is much more useful for us. So the mass dry is our payload, 5 tons let's say, or 10 tons, or 500 tons, or whatever you're trying to get into orbit. And what we were aiming for is mass T minus mass dry, because this leaves us with our mass of fuel. And now it's easy because we just minus both sides by mass dry. And that leaves us with an equation that will give us our mass of fuel. Don't worry if you don't understand this, because this is complicated rocket science. But if you're genuinely interested in this sort of maths, I seriously suggest you check out the Kerbal Space Program Wiki cheat sheet page, which was where I got a lot of the information for this video. And there it will give you all of the equations that you will need to be able to do your own calculations and write your own code. So now let's have a look at some of the other equations that we're going to use in our program. So now we're going to have a look at specific impulse, or ISP. Specific impulse is a measure of how efficient your engine is, and is commonly written as ISP. The combined ISP for your spaceship can be calculated from the ISP of each individual engine. And this is relatively simple if you've got 3 of the same engines, or 4 of the same engines, or whatever. If you've got the same engines, for example 3 Rapiers in air breathing mode, they produce 3,200 seconds of specific impulse. That means that even though you've got 3 engines, it's still going to produce 3,200 seconds of specific impulse. Where it gets complicated is if you've got multiple engines of different specific impulses. So let's say you've got a Rapier and 2 Whiplash engines. So this means that your combined ISP will be slightly different. Let's say our Rapier has 3,200 seconds and the Whiplash each have 4,000. So to find your combined specific impulse, you need to use this equation. Your specific impulse is equal to all of the forces of the engines, all of the thrust of the engines, all over the thrust of each engine over its ISP. And this seems a very complicated equation, and it's quite difficult to write in code because you've got to iterate over. So let's say the Rapiers produce 100 kilonewtons of thrust, and the Whiplash each produce 75 kilonewtons of thrust. So we add the thrusts together, 100 plus 150. And then on the bottom we've got 100 over 3,200. And the ones for the Rapiers, which are 75 over 4,000 seconds. And that's how you get your combined specific impulse. The last equation we need to have a look at is the thrust-to-weight ratio. And it's a very simple equation. Your thrust-to-weight ratio is equal to your force of your engine, or your combined engines, all over the mass of your spacecraft times gravity. And that's it. It's a dead simple equation, and it's just working out the ratio of your force to your weight, and that's its name, thrust-to-weight ratio. The last thing we need to have a quick look at is your total delta V possible. So let's say you've got an engine of 250 seconds of ISP. This is equivalent to a puff engine. So this is a very small engine, and it means you can only carry a certain amount of delta V. So it means that your engine will only be able to produce a certain amount of delta V. Even if you've got all of the fuel in the world, you will still only be able to produce this amount of delta V. For a PAF engine, this is 5,390 meters per second. The amount of delta V you can produce as a maximum increases as you increase your ISP. So, for example, a Dawn engine, which is the ion engine, can produce 4,200 seconds of ISP, which means it's incredibly efficient. And it means it can produce a maximum of 33,750 meters per second delta V, which is a massive amount of delta V. But it'll do it very slowly, which is why the thrust-to-weight ratio is important. If you're producing your delta V at a rate of 1 meter per second, it means it's going to take ages to do a burn, which has some bad consequences, especially if you're doing interplanetary burns or capture burns, but specifically if you're doing circularization burns. It means when you're actually burning, let's say your orbit is here, you're actually going to have to start burning before, which means you're actually facing towards the planet. This means it actually has a negative effect on your orbit, and this can cause huge problems, especially if you're doing interplanetary transfers. It's also important when you're trying to get off the runway, because if you don't have enough thrust-to-weight ratio, you just won't be able to pull up like the flight path for an SSTO. So now let's have a quick look at the code. So I've written this in Python 3.6 using a tool called PyCharm, which is something known as an integrated development environment, which provides a lot of helpful hands when writing programs. So if we start from the top, we can see we're importing math. That's just for some complicated equations that we need to do with rocketry. Get a few inputs as we go down. We either take new inputs for the rockets here, or we just leave them as is with the rapiers. We just need to grab a few more things like payload and engines, and then the target delta V, and then the gravity. And if you're using this, it's 9.81 for Kerbin, and it's all described in the program. So if we go into this function here, calculate fuel, by default it will do 10 epochs, 10 cycles, which is normally more than enough to calculate the right amount of fuel you're going to need. But occasionally you might need to increase that. But if you do need to increase that, it's likely that your plane will need a huge amount of fuel before it can fly. So here we go. So while I is less than or equal to epochs, so we're just looping through up to our epochs. We just say we're starting, and then this is for the different modes. So with mode 1, this is if you're filling the tanks of a rocket, and I'll demonstrate this later in the video, but this is for if you've got an existing rocket and you need to know how much fuel you need, and this equation here is for if you don't have a rocket and you're trying to figure out how many tanks you need. So this was our equation. Fuel is equal to e to the power of delta V over ISP times gravity times mass dry minus mass dry. That's what we did earlier in the video. And then we go down here, and this is just checking to see if our new result is the same as our last result. So if it is, it means the calculations happened and that we've got the right amount of fuel. So we're just bombing out of the loop here. And then, so if I equals epoch, so if we've got to the end of our cycle and it hasn't calculated it correctly, we just print calculation failed, increase epochs. And then we just print the amount of fuel you're going to need. Then we can do the thrust-to-weight ratios for the runway here and for in space. And then we just print those, and that runs. So if we run this, so this should run in any version of Python 3 from Python 3.1 up to 3.7, which is the current one. I prefer 3.6, it's just got a few more libraries that haven't been updated yet. So we can run through, so let's say we're just going to fill our rockets. We're going to leave it as rapiers. Let's say we've got 4 engines. Weight of the rocket is 30 tons. And then let's say we want 300 to get to the edge of the atmosphere, and then 1,500 to circularize. We're on Kerbin, so 9.81, and there you go, you can see it does it lightning fast. So it gives us the amount of fuel we're going to need, and it gives us some useful tips about our thrust-to-weight ratio. So if we feel that's too low, we can then go and increase our engines on our rocket ship. So now we've had a look at the code, let's have a look at how you can use it. So to install the program, you're going to want to go to one of the links in the description. There is a Python script in the description, so it will require a version of Python 3 to run, or you can download the .exe, which is a standalone version, so you don't need to install Python or anything. It will work straight out of the box, but you may get some problems with virus checkers, so if you do get problems, use the Python version, but you will need to install Python, and I will link a good tutorial in the description. So you're going to want to go to one of the links, and here we're going to use the exe version, and we're going to want to download this, and then we can have a look at this in the downloads folder. So we can see I've already downloaded this previously, so we can extract this using Windows Explorer. So we can go into it, and then we can do extract all, so you don't need WinRAR. So we can extract it, and then if we go back to downloads, it will be in a folder. So here we go. So it will come in looking like this, and you can then run the program, and that's all it is to installation. So when you run the application, you might find that Windows blocks it. Now this isn't a problem, it does do this. What you're going to want to do is go to more information and run anyway, and that should only be for the first time, and then you can use the program as normal. So now let's have a look at how you can actually use the program. I'm going to show you how we can use this program to figure out the amount of fuel that we will need to power a spaceship. So we are going to use the Elysium, the ship I showed off in the last video, as a demonstration. So for this we're going to want to go into Kerbal Space Program. So here we are, the Elysium. We're going to, for the Elysium, we've got this tank in the front, so we just want to get rid of that. So we want to figure out how much fuel it's going to take just to get us into orbit and get back safely. So if we drain all of the tanks, we then need to make a note of how heavy the ship is. So here we can see it's about 42 tons. And then we're going to head back to our program, and because we're filling up the tanks, because we've already got a spaceship, we go 1 for fill. We're just going to be using rapiers, and we have 10 rapiers. So the payload of the rocket was 42 tons. So let's go with 3,500 meters per second of delta V to get to the edge of the atmosphere. This is sort of the amount that you would want if you're starting off flying SSTOs. So then let's do 2,000 to circularize and deorbit. So we've got enough to go into some higher orbits, and we are around Kerbin, so 9.81 for the gravity. For the calculation epochs, unless the program tells you otherwise, leave it as 10. So there we go, we can see our calculation's been done. So we can see we're going to need 10.4 tons of liquid fuel, 46 tons of rocket fuel, and we can see our thrust-to-weight ratio here. Now these are working on the assumption that you're going to burn all of your liquid fuel on the way up, which isn't always the case. So you might want to put more delta V for your rocket mode in than you think you're going to need. Right, so now let's jump into Kerbal Space Program again. So we're going to want to fill up the liquid fuel first and make a note of how much fuel we need. So there we go, at the bottom you can see. So 10 tons. So that is 2,000 units of fuel. So then we can drain this tank out again. And we can have a look at how much these side tanks are going to store. So when you're filling tanks up in symmetry mode, they will fill both tanks up at the same time. So if we fill these up, we can see that it's going to store 8 tons in total, because rocket fuel is a combination of liquid fuel and an oxidizer. So we can see by adding those two together, we get 10 tons. We get 8 tons. So if we fill all of these up, we end up with 24 tons of rocket fuel. So then we just need another 22 tons to fill up the rocket. So if we fill this up to full, and we can see how much fuel this will store. So we can see it can store about 49 tons of rocket fuel. So if we just reduce this down a bit, that's almost bang on 46. So, and then we just need to fill back up the front with 2,000 units of fuel. And that will be enough fuel. And we can see that when we turn off the fuel, the liquid fuel, in these tanks, the fuel we're going to use, the amount of delta V we have, is very, very close to the 3,500 we put in. And you can always increase these slightly. So that's how you use it to fill up a spaceship. So now we're going to have a look at how you can go about building a spaceship. So let's say we're just going to use this cockpit. So this is our payload, the cockpit and the nose cone. We might also want to put some wings on as well, so we know that it's going to be slightly more than this in total. So we're going to want to go to our program again. So we're going to want to make a note of how heavy this is, so 1.1 tons, and then we're going to go to the program. So we'd leave this as 0 for normal. We're going to use rapiers. So let's say we're going to have one engine, and the payload of the rocket is 1.1 tons, but the engines weigh 2 tons each. So we say 3 tons. You round it to the nearest ton just to stop the program getting confused. Let's say we're going to use 3,500 meters per second to get to the edge of the atmosphere, and then we're going to want 1,500 to circularize. We're around Kerbin, so 9.8, and we'll just leave it as 10. So there we go, we can see how much fuel we're going to need. So we're going to need 0.68 tons of liquid fuel, and 2.5 tons of rocket fuel. And these are only rough, so you need to be careful with these. So we're going to want storage for about 1 ton of liquid fuel and about 3 tons of rocket fuel. So if we go in here, we can, if we snap on an air intake, and we can see how much fuel we've got there. So we've got storage for about 1 ton of fuel. So we want to drain this, and then we want to snap on another. So we want to snap on another tank behind, So this is going to be our rocket fuel, and we can see we've got storage for 4 tons of rocket fuel. So then we want to snap on the engine and put on some wings. And I'm not going to go into some of the complicated bits like the aerofoils and stuff, but we put some stuff on. So we can see that it's going to weigh about 5 tons with wheels and stuff. And that's just the base plane. So this includes the fuel tanks, but we're not with fueling, and the wings and the engines and all of the other gubbins on it. So now we've got a more accurate value for the weight of the spacecraft. What we can go do is go back into our program, and we can do fill mode, and we can say we're using rapiers. We've got 1, and the weight of our rocket was about 5 tons, so 3,500, and then 1,500, and we are on Kerbin, and 10 epochs. So there we go, we can see that we're going to need about 1 ton of liquid fuel and nearly 4 tons of rocket fuel. So we can then do the same process with this spaceship, and that will give you a similar amount of fuel. It will give you the right amount of fuel. And that's how you design a spacecraft using the calculator. I hope you've enjoyed this video. The code for this took quite a long time to perfect, and I hope that I will have saved you hours of work, because the maths behind it took a lot of working out and researching, and to my knowledge, I am the first person to have written a program to reverse the delta V equation. I've compiled it all into a .exe, so you don't have to install Python, but the Python script will also be on the website if you do have Python and don't want to install the executable. I've been Matt, and I will see you in the next video.